Hello and welcome to Minukuu tutorials. In today's tutorial, I'm going to show you how to perform two sample t-test in R or RStudio in case you're using RStudio for independent groups. Now, it's important to note that two sample t-test is simply a statistical test that we perform in order to compare the means of two given populations. Now, the primary condition is that these two populations must be independent. In other words, they must not be what? Paired. Being independent means simply that these two groups, or if you want, these two large populations must be what? Separate. Okay? They must be two separate groups. Okay. And now, from these two separate groups or two separate populations, we're gonna carry out our statistical test by means of what? Inferential statistics. For the simple reason that we cannot, let's say, we cannot calculate the mean of each of the entire population. That's why we resort to what? Sampling. And since we are going to do sampling, which means we are going to draw a random sample from each of the population. So we will draw a random sample from population 1 that we will name n of size n1, and we'll draw an equal random sample of size n2 from population 2. Now, based on these two samples that we've drawn from these two large populations, we can calculate the mean of each of the two samples and then try to infer or deduce whether there is a statistical significant difference between the actual population means. Since we don't have the capacity of what? Calculating the mean of each of the entire populations. That's why we resorted to what? This sampling. Okay. Now, there are conditions attached to carrying out t-test for independent groups, and we are going to look at these conditions in details. But to add to what I've just said about t-test, it's important to note that we don't only have two sample t-tests, but in some cases we could also have what we call a one sample t-test. Now, a one sample t-test is actually performed when our aim is to simply test or compare whether when our aim is to simply test by simply comparing the mean of our population of interest, so to a particular value. Okay, so for instance, we may be interested in trying to know whether the mean, since we cannot calculate the mean of a particular single population, we can just simply draw a sample, random sample from this particular population, and we would try to find out whether we would try to deduce, or let's say try to find out what you want to infer to know whether, let's say, from this particular sample that we've drawn from this larger population, we will try by statistical testing, that's t-test for one sample t-test, in order to know whether the mean of this particular population will be statistically significantly different from a particular value or predetermined value. For instance, we may be interested in knowing whether the mean temperature of women is statistically significant, or let's say is significantly different, in other words, less than or greater than 37 degrees Celsius. So in this case, we will perform a one sample t-test. We could also have another type of t-test known as a two-sample t-test for what? Dependent or paired groups. This is the case whereby the two groups that we are actually trying to compare, we are going to do the comparison based on a single sample. Okay, for instance, if we want to compare the effectiveness of two drugs, we can decide to administer these two drugs on the same population, or sorry, on the same sample drawn. Okay, so we have a sample of size, let's say 50, and on these 50 patients we're going to administer drug A, and then we will certainly have a washout period. Then after measuring the effectiveness of drug A, we'll have a washout period, and then we'll administer what? Drug B. Now drug A and drug B, though they are two separate groups, because we are actually going to test the effectiveness of drug A on the real population of people who take drug A, and we're going to as compared to the effectiveness of drug B within the real population of what? People who take drug B. So we have two groups. However, these groups are said to be paired, or these two populations are said to be paired because we are actually going to do our statistical testing based on a single sample. Now, in a case where the two groups, in a case where we are going to compare more than two groups, in other words, we are going to compare more than 3 means. So we have the mean of, let's say, population A, population B, population C, and even up to, or let's say in simple and short, when we are to compare more than two groups, in other words 3 groups, or if you want 3 populations and above, we cannot perform t-test, and in such a situation we resort to what we call analysis of variance test, also known as ANOVA. Now, I was supposed to have started my t-test series with, let's say, one sample t-test, and then finally to analysis of variances. But I'm actually starting my first series of tutorials on t-test with a 2-sample t-test because a Patreon, if you want, a loyal subscriber to Minukuu tutorials, suggested that I make this video. Okay, so please subscribe to my channel in order not to miss my future tutorials on the other types of t-test and even ANOVA, or analysis of variance test. Alright, so without much ado, we're gonna start our test, and we'll start by reading our data into R. Okay, and then we're going to follow these particular steps in performing our t-test. Now, the first step that we're going to look at has to do with what? Verifying whether the conditions of the test are met, because t-test is a parametric test. A parametric test is simply a test that is based on certain assumptions. Okay, generally based on in the case of t-test, it's based on the assumption that, you know, the two groups, or if you want, the two populations that we are going to compare, their means must be what? Normally, they must have a normal distribution. In other words, they should follow a normal distribution. And secondly, the variances of the two groups could either be equal or not equal. In the case where the variances are not equal, we perform a 2-sample t-test for independent groups for what? Unequal variances. In case they are equal, then we perform a 2-sample t-test for independent groups for what? Equal variances. Alright, so, and after you have verified that the conditions are met, now you're gonna examine or explore your data by graphical representation. Since here we are interested in comparing means, that's why we are doing t-test. So mean of population 1 as compared to the mean of population 2. Then the best way to represent what should I call it? The best way to represent the distribution of a quantitative, or if you want, the numeric variable, is often with a box plot. Okay, because with the help of a box plot, we are able to study the measures of central tendency. That is the, what do we call it, the median, you know, and then the quantiles, okay, of each of the groups. And then based on this, we can just examine on the box plot to see, you know, whether the mean of population, the median of population A is bigger or less than the median of population B. Now, based on these sample observations, we can now formulate our hypothesis on the real population of population A and the real population B, based on the sample means, just by drawing a box plot of the distribution of each of the samples. We can now try to deduce whether in the real population, so we can now formulate our hypothesis on the real population. And then we carry out our statistical test, our t-test, and then we finally do the interpretation. So starting with reading the data into R, the data that we are actually going to use is simply the sleep data. Okay, so the sleep data is simply a data set of 20 individuals, and these individuals were administered 2 different sporific drugs. Sporific drugs are simply drugs that are meant for, I think, for the induced sleeping or something like that. If I'm wrong, please correct me. Okay, so we simply, this data exists in R, so I'm simply gonna load it by using the code or the command data. So if, as you watch, you can also practice along with me, so you follow the same steps. The data is this data that I'm going to use is called sleep data, and it exists already in R. If you want to use your own personal data, you can also use it, there's no problem. Now, so to load this data set in R, I simply say data into brackets sleep into quotations, so I put sleep. Sorry, I think, yeah, sleep. And then I'll close the brackets. Now, if I should run this to load our sleep data. Now, if I should come down here and say print sleep, we're gonna see what sleep contains, the sleep data set. Now here it is. This is actually the sleep data set. So we have extra here. I think extra here represents the extra number of hours slept after taking the drug. Group here represents the drug, okay, or the medication that was given, the sporific drug that was given. Group A received a particular drug, group B received another drug. Okay, so we have 2 groups. Like I said, the 2 samples or the 2 groups must be equal. So we have a group of 10 people taking drug 1 and a group of 10 people taking drug 2. And then ID here represents simply the ID is just simply numbering of the total sample from 1 to 10. Sorry, 1 to 10 for the first group and 1 to 10 for group 2. All right. If you would also like to know more about the sleep data, it's very simple. Simply type question mark and then you write sleep. Now, if I should run this, R will tell us more about sleep data. Okay, so as you can see, they're saying what this from the data description. They are saying data which show the effect of 2 sporific drugs. I said sporific, soporific, not sporific. 2 soporific drugs. That's increase in hours of sleep compared to control. Okay, so maybe drug 1 is a control, and then drug 2 is maybe, I don't just really know. I don't know much about the data, but they are saying two soporific drugs, so which means drug 1 is a soporific drug, drug 2 is also a soporific drug on 10 patients. Okay, so in real sense, this particular data set is a paired data set, but we are going to treat it as let's say these groups are actually paired groups, but we are going to treat it as independent groups. Okay, because we only have 10 patients, and these 10 patients were administered the same, let's say one of the soporific drug, that's drug 1, and then we have another group which is not like a separate group, it's still the same patients receiving the next drug, but we're going to actually treat this data set because the example that I'm using is a pre-existing example for t-test for independent groups. In R, they use this data set to perform independent t-test, two sample t-test for independent groups, and they also use it to perform two sample t-tests for paired or dependent groups. So I'm going to do the same. So all right, there's no need reading all these details. You can do that at your own free time. So now let's continue. Like I said, when performing t-test, you must first of all, since it's a parametric test, it's based on certain assumptions or population assumptions, and these assumptions must be verified. That's what you must verify that the conditions for the test are met before you start doing the test, because the reliability, or if you want, the reliability of the test is based on these assumptions on the populations. And the first assumption is that the two groups or the two populations that we seek to compare their means must follow, each of them must follow a normal distribution or the Gaussian distribution. And secondly, it's also based on the assumption that the two populations have equal or unequal variances. Now I will show you how we can verify these two first conditions. Okay, but before we proceed, it's important to note that t-test, simply because t-test is used to compare means, then what that means is that we have two means, and we are going to compare the means of two groups. Now, when we talk about mean, we are talking about what? A quantitative, or if you want, a numeric variable. In our case, our numeric variable is what? Extra hours of sleep. Now, when we are talking about groups, we are talking about what? A categorical variable, because it's only a categorical variable that can give us two groups or more, yes or no. So in the case of two sample t-tests, we are simply going to have two groups. So we have a group 1, which will be what? Group 1, which will be all the individuals that took drug A, and then group 2. Remember that we are assuming that group 1 and group 2 were, let's say, independent groups. So group 1 actually took drug A, and group 2 actually took what? Drug 2. Soporific drug 2, soporific drug 1. So the group here will be what? A categorical variable with two responses, either drug 1 or drug 2. So it's dichotomic. So what that means is that the purpose of t-test is to is actually to study the distribution of this quantitative variable between the two groups. In other words, since we are talking about, we are interested in comparing the mean of extra hours of sleep within group 1, all the individuals who took drug 1, and the mean extra hours of sleep, or let's say compared to the mean hours of sleep of all individuals which took drug 2. But now the statistical test is based on the two real life populations, let me put it that way. But since we cannot study the entire population, like I said earlier on, Now we have decided to constitute a sample of 10 individuals from the population of people who take drug 1 and 10 individuals from the population of people who take drug 2, and based on these two samples we are able to deduce or infer whether in a real population the mean extra hours of sleep of people who take drug 1 will be equal to the mean hours of sleep, extra hours of sleep for the population of people who take drug 2 in the real world. This is the purpose of the test. Now, without speaking much, we're gonna head on to performing the test. Like I said, we're gonna first of all verify the conditions, and the first condition to verify is whether the two samples have what? They follow a normal distribution. Okay. Now, there are different ways of testing to know whether a particular population or a particular sample follows a normal distribution. One of the ways is by QQ plot. QQ plot will simply you see a diagonal line, and then on this particular line we will have a plot of the sample quantiles against theoretical quantiles. Okay, and now when we look at the sample distributions or the sample points, when the sample point, we will look at it graphically, so there's no need explaining. And apart from the QQ plot, we can also do what we call a test called Shapiro-Wilks test of normality to also know whether, so we can do both. And then the second condition is to verify whether the two groups have equal variances, and to do this you simply do the test called the variant F test or Fisher's test of variances to know. So in a case where we find out that, let's say, the two groups have equal variances, then we can do t.test for equal variances. In case they have unequal variances, then we do t.test for unequal variances. Now let's start with the first one, which is whether the two samples have let's say what, normal distribution. Okay, for the two groups, not the two samples. So to test whether the two groups or the two populations have normal, they follow Gaussian or normal distribution. How do we do that? Let's start with the QQ plot. So let's start with QQ plot. Okay, we will start with QQ plot. By QQ plot. Okay, now if you do your QQ plot is very, very simple. You need a package called ggpubr. I cannot even pronounce it. So you simply install the package. Let's say you say install .packages into brackets, into quotations, then you put this package there, ggpubr, then you put the quotations, close the bracket, and then you run this to install your package. Now I guess I might have already installed this package, so I might just load it in my library. I think, am I sure this is actually the right package? Sorry for the interruption. So I did not actually put the brackets. I selected the code without, so let me add a bracket, then let me run it to do our installation. Sorry, let me do it again. Select install.packages into brackets ggpubr, then you run this to install the package. You select your crown mirror. Since I'm in Paris, let me pick Paris. Let me pick, I cannot find Paris. It's weird, I don't know. France. It's okay. Then pick this one, and then I pick OK in order to install the package. Now I'm waiting for the installation to be done. Alright, so as you can see, the package has been successfully installed. Now simply load it in my library by simply saying library. This package contains the QQ plot code. So it says library into brackets ggpubr in order to load the package that we've just installed. Okay, sorry, I don't know why I keep selecting without the, well, let me just put brackets here. Okay, so our package has been successfully loaded. Now after loading the package, we're gonna do our QQ plot. It's very simple. So it will actually be we will try to, they are saying what, whether the two sample groups x1 and x2 to be compared follow a normal distribution. Okay, so x1 must follow a normal distribution and x2 must follow a normal distribution. Here the sample groups that we are talking about are simply group 1 and group 2. That's of the people that took the drug. So group 1 and group 2. So let's quickly do that. Now how do we do that? It's very simple. Let's do our plot. All that we have to do is to we start with, first of all, the group 1, okay, to know whether the group 1 follow a normal distribution or a Gaussian distribution or not. Now to do the plot, we simply use the code ggqq plot into brackets. Then we use I don't know what to say. We're gonna use sleep. So we are going to do the ggqq plot first of all for these 10 individuals. That's the 10 individuals that took drug A or drug 1, sorry. So we will say sleep, then we use the $sign to select what, extra, which is our variable or our numeric variable of interest, extra. So, or if we don't want to always use, let's say, the $sign, because using the $sign is gonna waste us a lot of time, because if I wanted the variable extra, then I could have just written extra instead of writing sleep $sign extra. So to prevent this, let's attach sleep, the sleep data set. So we simply attach the sleep data set, attach into brackets sleep. Okay, now what that means is anytime I want a particular variable within sleep data, I simply go for the variable instead of writing a sleep that variable. So now I've done that, and instead of writing sleep extra, I'll just write extra. But we want ggplot for extra for which group? For only the group or the group of individuals that took drug 1, which is 10 people, right? So we're going to use square bracket to select. So we say group, which is the group of individuals here, group, then we use $= sign to select 1. Then we close the bracket, then okay. So this code simply means we want a ggplot for the extra hours of sleep for what? Group 1. That's the 10 individuals that took what? Drug, soporific drug 1. So let me run this and you see the ggplot for this particular group. Perfect. Now look at the ggqq plot here. And what can we say about this particular plot? Like I told you, it's simply the sample quantiles plotted against the theoretical quantiles. And now we have this diagonal line drawn here, and when we look at the sample points, we will realize that the sample points are bouncing randomly along what the line. Okay, they are along the line. They are this line here. They are bouncing randomly along this particular line. So we haven't seen any kind of, so you see that they are randomly distributed along the line. So this suggests that the group 1, which is the 10 people, the sample of 10 people that took drug 1, the sample distribution is actually normal based on the QQ plot. So we can assume that the real population of people who take drug 1 actually follow a normal distribution based on our sample. Let's do the same for group 2. So I'll simply copy this and repeat the process. So I'll say, let me copy this, get down, paste it here, and this time around we're going to do it for group 2. So I'll simply say it's the same thing, but now we want it for group 2. If I had wanted, I would have used the parametric command in order to put the two graphs on the same, but we are not interested in comparing the two graphs. Our aim is simply know whether each of the two groups actually follow a. So this is for group 2, as you can see. If you want, let me close this one and take it again, and you will see it is for group 2. Okay, so group 2, it's almost the same thing. We can see that like all the individuals, it's always best when the individuals fall directly on the line. Like if you have all the individuals falling directly on the line, that's always perfect normal distribution. But in our case, not all the individuals are directly on the line, but we can see that even the individuals are very close to the line here, and at the same time they are randomly bouncing along the line. We don't have any kind of extreme sample values. So this also suggests that the second group follows a normal distribution. Apart from this, we can now conduct what we call the Shapiro-Wilks test of normality. That would be, because graphically looking, it is sometimes hard to interpret, okay, based on the QQ plot. So let's quickly do the Shapiros test, or the Shapiro-Wilks normality test. Okay, that one too is very simple. To do the Shapiro-Wilks test, you simply have to use you need a package called car, C-A-R. So let's install the package now. We've done QQ plot. Now let's look at the second method, which is by Shapiro-Wilks test of normality by Shapiros test, or if let's just say Shapiros test. Shapiros test. Now for this particular test, we need a package called car. So let's install the package. You simply say install packages into brackets, then the package is called car, like car. Okay, now let me install this package quickly. Okay, the installation is done, as you can see, and then I'll load it in my R library by simply saying library into brackets car. We close the brackets, and then let's run this to load the package car. And after the package car is loaded, we can simply go ahead and perform our Shapiro-Wilks test of normality. So it's very simple. We simply say Shapiro, the command is called Shapiro. It's interesting. So we say Shapiro into brackets then we are actually going to do it for both groups, right? So we're gonna say extra. So our quantitative variable here, we are going to look at the sample, whether the distribution of the 10 individuals that took the what should I say, the distribution of the whether the distribution of the extra hours of sleep. So extra, okay, distribution of extra within the I don't know how to put it. So we say extra, whether distribution of extra follows what? We have to look at whether like the distribution of just like what we did here. So we have extra here for sample 1, whether it follows so group 1, so we will do whether distribution of extra whether the distribution of the extra hours of sleep within the, or let's say among the individuals that took drug soporific drug 1 actually follow the Gaussian or normal distribution law. So we're gonna, just like what we did, we're gonna do the same thing here. So you use the square brackets, and then we say group is equal to what? 1. Okay, and then we close the square brackets. So group is equal to 1. Let me close the square brackets, and then I'll close the bracket. Let's see what it will give us. Why is it saying? It's saying what? Error in Shapiro, could not find the function. Is it that I haven't spelled Shapiro correctly? We could not find the function Shapiro. Oh, let me make this one capital S and C. Probably I wasn't supposed to. Let me try this with capital S. It's still giving me an error. I'm coming. I have to look for the, I'm so sorry for that. It's actually shapiro.test and not Shapiro. Simply Shapiro. It's shapiro.test. So let me correct it. Sorry for that. Shapiro.test. Okay. Now let me run the code again. Okay, and it has actually performed the Shapiro test, and it has given us a p-value of 0.4. So the null hypothesis for the Shapiro test is that the, what do you call it, the sample follows or a Gaussian distribution or a normal distribution. The alternative hypothesis is that it doesn't follow. So looking at our p-value is greater than 0.05, which means we cannot reject the null hypothesis, which suggests that the extra hours of sleep among or within the group of people that took, the 10 individuals that took soporific drug 1 actually follows a Gaussian distribution. Let's do the same for the group 2. So I will simply copy this particular code and then put it down here, and we're going to name it what? Shapiro.test, and let's just put group 2 here. So I put 2 here. Let me run it. Okay, now that gives us also a p-value for group 2. That's the distribution of the extra hours of sleep within the group of people that took soporific drug 2 also gives us a p-value of 0.3, which is also greater than 0.05, which suggests that we cannot reject our null hypothesis, which means the two groups, sorry, the two groups, or if you want group 2, not two group, the group 2, also the sample group 2 also follows what? A normal distribution. So in terms of normality of the distribution of the two groups, here we are saying X and Y. Let me say group 1 and 2, so that we will not get confused what X and Y are. X and Y here we are referring to group 1 and 2. Actually, both groups actually follow what? A normal distribution. Now, what that means is that the condition of the test in terms of normality of the distribution of the two groups have actually been met. The two conditions have, sorry, the condition of normality has actually been met for the two groups. Now we move on to equality of variances. To test the equality of variances, usually, just to tell you something, there is an alternative test that we could have done in order to compare the variances of populations, which is the Z-test. However, the Z-test requires that we know the standard deviation of our populations. So often than not, it's hard to know the standard deviations of the populations. And when we don't know the standard deviations of the population, the best method to use is the t-test. Another indication of the t-test is when we have, let's say, some very little or small sample sizes. Usually, because when we have a very small sample size, often than not, the distribution of it's always hard to tell where the distribution of to tell from these samples of from these little samples, or if you want samples of small sizes, we cannot tell whether the population distribution will follow a normal or a Gaussian distribution law. So for this reason, when we have a sample size that is less than 30, we always prefer carrying out a t-test. But maybe we have a sample size of more than 30 or equal to 30, then at that point we can assume that the distribution of our samples of our populations would follow a Gaussian. It'll follow a Gaussian or normal distribution. So this is why t-test is preferable, because t-test, first of all, doesn't require knowing of the standard deviation of the population or the populations, and secondly, for smaller sample sizes, t-test is still favorable. Okay, now now to test whether the variances of the two groups are equal or not, we're going to use the Levene's test. Okay, Levene's test for homogeneity of variances. And now this test, to do this particular test, you also need the same once again you need a package called car. So you make sure you repeat this particular procedure, install the packages in the brackets, car, and then you load it in your library. So since I've already installed it, there's no need repeating. I'll just load it once again. I've actually loaded it, there's no need repeating, but I'll just say library into brackets, then you write car, then you load it. After loading it, now you can go ahead and perform your Levene's test for homogeneity of variances. So, and now to do this, what the purpose of verifying whether the variances are equal is for us to either perform a t-test, or let's say a two-sample t-test for independent groups with equal variances or unequal variances. So to do the Levene's test, it's very simple. After you have loaded the package called car, you simply say Levene. Levene is something like this, and then you simply say Levene test. Okay, you make sure the test is written with capital T, but the rest of it is in small letters, into brackets. Then we're going to say the variance of extra, which is the extra hours of sleep. So we write extra separated by what? The group of soporific drug taken. That's group 1 or 2. So separated by group. And for the Levene test for homogeneity of variances. Homogeneity here simply means equality of variances. Now, the null hypothesis is that the two groups have equal variances, and the alternative hypothesis is that the two groups have unequal variances. So let's run Levene test and see what happens. Now, from the Levene test results, we can see clearly that our p-value is actually 0.6, which means it's greater than 0.05. Since the p-value is greater than 0.05, it means we cannot reject the null hypothesis, which suggests that the two populations have what? Equal variances. Now, since the two populations have equal variances, then it means, or the two groups have equal variances, we're going to perform a t-test for what? Equal variances. And we can still move ahead and examine our data, to see, let's say graphically, can we say based on what we've just done, we have realized that the two groups have equal variances, okay? But we can still go ahead and explore our data to see whether, for instance, based on, let's say, by a box plot, we will be able to tell whether, for instance, the median of group 1 is greater than that of group B, and then we will be able to formulate our hypothesis, and then do the t-test. So now, based on the conditions that we've just verified, we've been able to prove that the distribution of the two groups are actually normal, and that is perfect. We've also, thanks to Levene test of homogeneity or equality of variances, we've been able to conclude that the two groups have equal variances, which means we're going to perform a t-test for equal variances. Now, let's just explore our data, as I was saying, using a box plot. So to explore our data using a box plot is very simple. We simply say box plot into brackets, then we use extra, which is the extra hours of sleep separated by what? Group. Okay, so when we do this, we'll actually draw the box plot for each of the groups on the same plot. Okay, so now looking at group 1 and 2, what can we see? Looking at our box plot, we can see clearly that group 2, looking at the median for group 2 is above what? That of group 1. If you want to know, like based on the box plot, we can just see clearly that what that means is that the group of people that took soporific drug 2 actually have, let's say, higher extra hours of sleep compared to the group of people that took the drug 1. So you see that drug 2 have higher extra hours of sleep. That's why the median is around 2, whereas the median for group 1 is around. If you want, we can just look at this. You just say summary. If you should say, for instance, summary, statistical summary. So you say summary into brackets, extra, and then we simply select group 1. Okay, let's say group 1. So we say group is equal to 1. So the purpose is for us to see so if I should, let me run this and also repeat the same thing for group 2, and you're able to see clearly what I'm trying to say. So let's repeat this for group 2. Now let me paste this and I'll do it for group 2. So it will give us the statistical summary for each of these groups. Let me run these two codes. Now looking at so you realize that what's the median for group 1 is what? 0.35, whereas the median for group 2 is almost 2, right? 1.7. So this suggests that based on these results, we can see clearly that, so based on these results, we can formulate our hypothesis that, you know what, let's say the median hours of sleep, we can formulate our hypothesis that, we will formulate our hypothesis that in a real population of people that take drug 1, soporific drug 1, and a real population of people that take soporific drug 2, we can formulate our hypothesis that the median extra hours of sleep for people who take soporific drug 1 will be greater than that of what? Will be greater than that of the median hours of sleep for people who take drug 2. So let's formulate our hypothesis. Let's formulate our hypothesis. Our hypothesis, null hypothesis H0, will be that the mean 1, that's the mean of population 1, will be greater. So mean of population 1 will be what? From what we have just observed based on our sample, we realize that mean of population 2 is greater than that of population 1. So mean of population 1 will be less than mean of population 2. And now the alternative hypothesis will be that H0 will be that the mean of population 1 will either be what? Greater than or equal to the mean of population 2. So since it's greater than or equal to, this suggests that it will be a two-sided test, right? Because if it's greater than or equal to, if it were to be less than, then less than is purely one-sided. If it's greater than, it's purely one-sided. But if it's greater than or equal to, then it means it's what? It's two-sided. So based on the alternative hypothesis, we can say it's a two-sided test. Okay. And now we just move ahead and perform our t-test. Okay. Now, to perform our t-test is very simple. We're going to use the t.test. So, and it's very, very simple. So we say t.test for t-test, t.test into brackets. Now we're going to write our variable of interest, our dependent variable, which is our extra hours of sleep. That's the numeric variable. So we say extra separated by what? Extra separated by group. Okay, so write group here, and then after which we write comma. Now we're going to put the mean difference, or let's say the mean difference of the groups, or let's say differences between the means, the two means. Okay, now if you notice, what we've written here is that if we are saying, for instance, you see, but based on our hypothesis that we formulated here, we are saying that mean 1 is less than mean 2. So if we are saying mean 1 is less than mean 2, then it means, what that means is that mean 1, let's say mean 2 minus mean 2 minus mean 1 will be what? Mean 2 minus mean 1 will be greater than 0. That's what we are saying. Since we are saying mean 1 is less than mean 2, then what that means is that the difference is, if you want, mu stands for difference between the mean. Okay, so differences between the mean 1 minus mean 2 will be greater than what? 0. Otherwise, if mean 1 were to be equal to mean 2, then what that means is that the differences would have been 0. So it's important that you will have to give a particular value for this particular difference, since we are doing a two-sided, our test is actually a two-sided test. Okay, however, based on our null hypothesis, we are suggesting that mean 1 will be greater than mean 2. So we have to, statistically, we have to give a difference. Okay. So we could say, for instance, the difference should be 5. Okay, so we could say that the difference between mean 1 and mean 2 should be, let's say, 5. Let's assume that mu, for instance, the difference between these two should be equal to, let's say, 5. Okay, let's just say it should be equal to, let's say, 5, for instance. Or better still, we can look at, but the problem is that this particular, the means, the differences of these means here is not actually the, it's actually the population mean. So we cannot, this value that we are giving is actually just an assumption, and it's not a precise value, because the difference between m1 and mean 1 and mean 2 here, we are not talking about sample means, we are talking about the population mean. So we could assume that the difference between m1 and m2 should be 5, since our null hypothesis is that mean 1 is less than mean 2, based on after the exploration of the data that we did. We just noticed that the median of group 1 is above that of group 2 is above that of group 1. So we assume that mean of group 1 will be less of, within the rate population, mean of group 1 will be less than mean of group 2, which means the difference, which is mu here, stands for the differences between mean 1 and mean 2 and mean 1 will be greater than 0. Now we are assuming that this difference should be 5. If we had assumed that within the real population our null hypothesis were to be, let's say, mean 1 and mean 2 were equal, if we had assumed that, then in that case we would have kept mu, which is the mean differences between mean 2 and mean 1, would have been equal to 0. But since we haven't done that, we are assuming that this particular mean here difference should be 5, for instance. We cannot come and calculate the sample difference to use it, because that would not make sense, because this means that we are talking about are not the sample means but the real population means, which we do not know. Okay, so we just say mu here should be equal to 5, but it's based on certain reasons. Before you can, I'm just assuming, because this is just an ordinary test, but usually when you are doing this you have to base your assumption. Why are you not saying but we could have said, in order to prevent this, if we don't want to give any value to this, then we could have changed our hypothesis. Okay, for instance, based on, let's say, looking at these values, we have one of them is what, the median, for instance, is 0.3 and 1.7. we could have assumed that these are equal, which means we will not be forced to give any value for the difference. So I could have assumed that, okay, mean 1, so let's change it. We could, just looking at a sample, we could have assumed that no, this is not going to be there's no any significant difference between, let's say, remember this is the median. The median is not the same as the mean, but we are just observing, exploring our data to be able to formulate our hypothesis. So somebody could say, based on the medians 0.35 and 1.75, there's no any significant difference. So we could have just assumed that m1 should be equal to m2. In that case, the difference between mean 1 and mean 2, the mean difference would have been what? m2 minus m1 would have been equal to what? 0. Which means, and if that's the case, then what that means is that this one will either be less than or equal to. So instead of mean 1 would have been what? Less than. In other words, it would have been less than or what? Equal to. It would have been, if we are saying mean 1 is equal to mean 2, then the alternative hypothesis is that mean 1 is not equal to mean 2. In other words, it's either less than or greater than mean 2. So it's either less than or greater than what? Mean 2. I cannot write the not equal sign, or let's write it not equal to mean 2, which means it's still two-sided test. And in that case, this one will put the difference between mean 1 and mean 2 to be what? 0. Since we cannot, I don't want to assume, if not, you ask me, why have I decided that the difference between the two population means should be 5? Statistically, I cannot tell, because this sleep data, I don't have any prior knowledge about, in-depth knowledge about what the data is, and then what was, let's say, each group, the two soporific drug is based on certain clinical assumptions that we can say, okay, the difference should be this or that. I cannot tell. So I've decided to change my mind by saying, you know what, let's make mean 1 to be, let's assume that mean 1 and mean 2 are equal, which means we're going to do a two-sided test for unequal what means. Alternative hypothesis suggests that the two means are unequal, and by so doing, if our null hypothesis that the two means are equal, then what that means, the difference will be what? 0. So we just simply put a difference between mean 2 and mean 1, which is mu, here will be equal to 0. And after which, it's important to right now indicate the alternative hypothesis. So the alternative hypothesis, we just write alternate will be equal to, then since we are doing a two-sided test, we write into quotations two-sided. Okay, then we close the quotations, then we put comma. And now in a case where you are doing, for instance, a one-sided test, let's say, for example, if it's a superiority or inferiority test, I don't want to go into the details. If, let's say, the alternative hypothesis were to be greater, okay, so let's assume that we set mean 1 for, let's assume that we had said mean 1 was less than mean 2, then it means, or let's say mean 1 was less than or equal to mean 2, then the alternative would have been that mean 1 would have been greater than what? Mean 2. So if that were the case, then we would have written here alternative it would have been equal to greater, we have just written here greater. If the alternative hypothesis is less than, then you write what? Less than. But if it is less than or equal to, then it becomes two-sided. If it is not equal to, which means it's either less than or greater than, based on the alternative hypothesis, then you put two-sided. In our case, it's not equal to, which means it's either greater than. If we are saying alternative null hypothesis, mean 1 is equal to mean 2, alternative hypothesis will be what? Mean 1 is not equal to mean 2. In other words, it's either less than or greater than, which means it's two-sided. If we had said mean 1 is less than mean 2, it means alternative will be what? Mean 1 is greater than or equal to mean 2. It's two-sided. If we had said mean 1 is greater than mean 2, then alternative hypothesis would have been mean 1 is less than or equal to mean 2. That one will also be two-sided. But when it's just less than, then it becomes one-sided. When it's just greater than, on the alternative hypothesis, if it's just greater than, it's one-sided. If it's less than, it's one-sided. If it's less than or equal to, in other words, not equal to, means then you put two-sided. So I'll put two-sided here. So if it's less than, then you write here less. If it's greater than, you write greater. If it is less than or equal to, or greater than or equal to, or not equal to, in other words, greater than or less than, then in that case you put two-sided. And after which you also put, generally by default, the confidence, the level of confidence is usually 95% by default. So you just have to, but if you want to change it, you could change it. So you just say conf is equal to 0.95. This is the default. But if you want, you could have increased it. If you are saying 95%, it depends on your alpha. If you are taking your alpha risk to be 0.05, then conf will be what? Level of confidence will be 95%. but based on your assumption. If you are taking, for instance, 10, then your conf will be 0.9. So it depends on your risk alpha or your alpha risk. That's the risk of rejecting the null hypothesis when there's no actually difference. Okay, and after which you have to specify, because based on our test that we did, we came out and said that the variances of the two groups are equal based on the Levin's test that we did. So we have to say var dot equal is equal to true, because the variances are actually equal. So true. Okay, so variances are equal. So if you say variances are equal, var dot equal are equal to what? True. And after which it's important to indicate, like I told you earlier on, we can have t-test, let's say 2 sample t-test for independent groups, and we can also have 2 sample t-tests for what? Paired groups. So you have to indicate whether paired is equal to false or not. In our case, we are doing independent groups, so we have to indicate that paired is equal to false. You just write F, it's okay, and then you close the bracket. Now let's run this to perform our t-test. Okay, after running this, here are the results. We have a p-value of what? 0.07. So a p-value of 0.07 is actually greater than 0.05. Now, what that means is that we cannot, since the p-value is greater than 0. Look at the p-value is greater than 0.05, we cannot reject the null hypothesis. Okay, but not rejecting the null hypothesis does not mean that we have accepted the alternative hypothesis. It could be that our test, there's actually a statistically significant difference. However, our test power was not enough to bring out this difference. Maybe we had a very small sample size of just 20 people or whatever. So remember, by default, the test power here is actually 80%. Okay, all right, because our beta will be our beta risk, or will be taken as by default is 20%. So the test power will be 80%. Now, having reached this point, let's still continue with the interpretation. So with the interpretation, p-value, we realize that based on our test, p is actually greater than 0.05. So since p is greater than 0.05, then what that means is that since p is greater than 0.05, we cannot reject the null hypothesis. We cannot reject the null hypothesis, and if we cannot reject the null hypothesis, then we cannot conclude. We cannot conclude that there is a statistically significant difference. A statistically significant difference between the mean hours of sleep, the mean extra hours of sleep, between the mean extra hours of sleep of the population of people assuming soporific drag 1 and that of drag 2. Okay, now apart from the p-value, there are other interesting stuff that we can look at. Now we have what we call this particular confidence interval here. The confidence interval here is actually based on 95% confidence level. So this confidence interval here is actually the difference, it's actually the confidence interval of the difference between M1 and M2. So here I said M2 minus M1, but it could have been, let's make it M1 minus M2. Okay, so M1 minus M2. In either case, if we are saying M1 is equal to M2, then M1 minus M2 or M2 minus M1 will be give us what? 0. It's as simple as that. So M1 minus M2 here, it is suggesting that the difference is found between -3.3 and 0.2. This particular difference, MU, the real value for MU will be found between this particular brackets, -3.3 and 0.2. That's the real value. That's why I did not want to give any fictive value, because I don't know the real value. So I rather did reformulated our hypothesis, and now it's suggesting that the real value or the real difference between these particular two populations will be found between -3 and positive 0.2. And apart from this, we also have the mean of a group of people that took drug 1 and the mean extra hours of sleep for a group of people that took drug 2. Thank you so much for watching, and